Good morning, everyone. So, last lecture we were seeing uh, reliability, system reliability, and that we have seen one example. So, let's see few more example. So, in that context only. So, example two. So, consider three components: C1, C2, C3 with reliability R1, R2, and R3 connected in series. So these are connected in series. Find the reliability of the system where R1 is equal to 0.2, R2 is equal to 0.3, and R3 is equal to 0.4. So since the components are assumed to act independently, we can clearly write that reliability R is equal to R1 into R2 into R3. So this is the question. Now we are solving it. So we know the formula, that is total reliability is multiplication of all the reliabilities. So this will be zero point 0.2 into zero point 0.3 into zero point 0.4. So this will be equal to 4 3 12 to 24. So it will be 0.024. So the reliability has dropped from minimum, the minimum reliability was 20%. So it has dropped from 20% to 2.4 percentage only. So there is or 1/10 of the reliability. So now let's see another example. Example 3. So what is the system's reliability at 700 hours for a parallel system? So the time period T is given here. That is 700 hours for a parallel system. So 700 hours for parallel system. Component failure data is as below. So data is given for component failure. So that is failure rate of A, that is lambda A is given, that is 0.000007 failures per hour, and failure rate of A is A, reliability of B is given. So reliability of B is given as 0.92, and MTTF of C is given, so that is 1400 hours, and reliability of D is given, that is 0.85. So mean time between failures. Now we need to find all the reliabilities. So we need to find all the failure rates before finding the total reliability. So the failure rate of A, RA, will be equal to e raised to minus lambda t. So it will be equal to e raised to minus 0.1237 uh, 1237. So it was failures. So this failures per hour divided by, sorry, multiplied by t. Time t is 700 hours. So this will be equal to uh, e raised to, so two zeros 1 2 will be here, so 0.07 into 49, so this will be equal to 0.6126. Now reliability of B is given. Now for C, so we need to find reliability of C, so that is e raised to minus lambda t. So but we don't have lambda here, we have MTTF, that is mean time between failures. Now we know that MTTF is nothing but 1 upon lambda, so this will be equal to 1 divided by 1400. So that is, so lambda will be equal to uh, sorry this is 1 upon lambda, and we have MTTF is equal to 1400. So lambda will be equal to 1 divided by 1400. So this is the failure rate, that is 1 upon 1400. So this will apply here. So RC will be equal to e raised to minus 1 divided by 1400 multiplied by t. Now what is t? T is 700 hours. It will be 700. This will be equal to 0 0 cancels, 7 1 is 7 2 0. So this will be equal to e raised to minus 1 by 2. So it is e raised to minus 1 by 2. So this is equal to 0.6065. So we have got RA, RC and RB and RD are given. So now we can find the system reliability. So we know that the system reliability R is equal to 1 minus RA into 1 minus RB into 1 minus RC into 1 minus RD. It is multiplication of failure rate. So it is 1 minus 0.6126 into 1 minus 0.92 into 1 minus 0.6065 into 1 minus 0.85. So the total reliability will be equal to 0.998. So it is 99.8%. We can call it as 99.8% reliability of the whole system. So as you can see that in parallel system the reliability is higher than in the series system. So now let's see another topic, that is reliability point process. So that is reliability point process. So reliability point process. So point process model is developed to assess the reliability of a new designs which are variants of an existing product. So if any product is a variant of an existing product, so on that model the reliability is examined. So the model is Bayesian. So the model is Bayesian and makes use of existing expert judgment. Prior distributions are used to assess the number of inherent weaknesses introduced. So inherent weaknesses introduced through evolution of design. So the enhancement of the design will be experienced through a growth process. So here the enhancement of the design will be experienced through a growth process where failure information is gained about the new design and corrective actions implemented in order to measure reliability. So so it goes through growth process. The real life objects are operating in a changing random environment. One of the ways to model an impact of this environment is via external shocks occurring in accordance with the stochastic point process. So the Poisson, so the Poisson's process, so the Poisson's process, that is homogeneous and non-homogeneous. The renewal process and their generalizations are considered as models for external shocks affecting an operating system. So this is and generalizations are considered for models for shocks affecting an operating system. So the models which have been applied to repairable systems, so models which are being applied to repairable systems are stochastic point process and differential equations. So for this system the models are stochastic and are differential equations. So a stochastic point process, what it is, so it is a mathematical model. So stochastic, let me write the spellings. Stochastic, so it is a mathematical model for a physical phenomena characterized by highly localized events distributed randomly in a continuum applied to repairable system. So it is a mathematical model. So it is a mathematical model for a physical phenomenon. So it is a mathematical model for physical phenomena characterized by highly localized events. It is characterized by highly localized events. So applied to repairable system. The continuum is time and highly localized events are failure which are assumed to occur at instance within the time continuum. So various point process models are. So let's discuss the various point process models. The first is non-homogeneous Poisson's process. So that is non-homogeneous Poisson's process. So this non-homogeneous Poisson's process models are primarily used for modeling and analysis of failure data. So it is used for modeling and analysis of failure data, modeling and analysis of failure data for repairable system, failure data for repairable system, repairable system, for which repaired units are exactly, for which the repaired units are exactly the condition as they were just before the failure. So repairable system for which repaired units are in exactly the condition as they were just before. So a counting process uh, is said to be an homogeneous Poisson process with intensity if number one, that is so there is a counting process of n of t comma t is t dash t dash equal t dash 0. So first condition is that if n of t equal n of 0, then n of 0 will be equal to 0. So what does this mean? So this means that when time t equal to 0, so n will be 0. So then second condition, that is n of t when t is greater than equal to 0 has an independent increments. So it has an independent increments. Then third case, that is probability. So probability of n t t plus delta, it will be equal to 1, which will be equal to lambda, which will be equal to lambda t. So here when n number is equal to 1 between time t to t plus delta t, then the probability will be equal to lambda t, lambda that is function of time, plus o that is function of delta. Now the fourth probability, that is probability when number of items in interval of time t to t plus delta is greater than equal to 2. So when number of items n is greater than equal to 2, then the probability will be just 0, sorry, o delta. So the reliability function of a process r with respect to s and t will be equal to e raised to minus delta into t minus s. So the reliability could be constant over time if the intensity function, so the intensity function is delta t, is a constant, then the process reduces to a homogeneous Poisson process. So if this is constant, so it reduces to homogeneous Poisson's process, HPV. So HPV is a sequence of independent and identically exponentially distributed uh, XIs where non-homogeneous Poisson's process X's are neither independent nor identically distributed. A non-homogeneous process, a non-homogeneous Poisson process, that is an HPP, is characterized through its cumulative intensity dt function that is AT. So that is AT, which will be equal to 0 to t lambda of x dx, or by its time derivative, that is delta t, which gives the instantaneous rate of failures. So this is one model, 4-point process model, that is non-homogeneous Poisson process. Now we will see a second model, that is power law process. power law process. So the widely used NHPP. So the widely used NHPP is the power law process. So that is power law process. So sometimes called V-Bull process also. It is also called V-Bull process, whose intensity lambda t is given by some empirical relation, that is beta by theta into t by theta raised to beta minus 1, where theta is greater than 0, beta is greater than 0, and t is also greater than 0. So this is in some empirical relation, but there is no proof of this. Just a relation is given, it is beta by theta into t by theta raised to beta minus 1. So for beta equal to 1, so for beta is equal to 1, the process reduces to homogeneous Poisson's process. That is, it will reduce to homogeneous Poisson's process. So when beta is equal to 1, then as you can see, the lambda t will be equal to, so 1 minus 1 0, so this term will be eliminated, because anything raised to 0 will be 1, and this beta will be 1, so it will be 1 upon theta just. So it will be homogeneous Poisson's process. Otherwise, PLP produces a model for a system whose reliability changes as it ages. So if beta is less than, so if for beta is greater than 1, it models a deteriorating system, and when, so this will be a deteriorating system. So when beta is greater than 1, so this will be greater than, so this term will increase, and this term will remain as a constant. uh, so uh, therefore this lambda, so this model will be deteriorating, while when beta is less than 1, so when beta is less than 1, so it provides a model for reliability growth. So this will provide a model for reliability growth. So this will provide a model for reliability growth. So when beta is less than 1, so this term will reduce, and this term will be higher, or it will be greater. So it will provide a reliability growth model. So this was the second point process model. Now we'll see a third point process model, that is the renewal process. So third model, that is renewal process, that is RP. Renewal process, that is RP. So a renewal process uh, is defined as a sequence of independent identical distributed non-negative random variables. So what I have said, so of a sequence of independent then identical distributed and non-negative random variables, that is x1, x2, x3, and so on. So it should be independent, so it should not be dependent on each other. Then second, it should be identical, so it should be similar. Then it should be distributed over all the plane. Then it should be positive, it cannot be negative. Then it should be random, so it should not be dependent on each other, so it should be random anywhere. So in this case, the system after repair will be good as new. So after in this case, the system after repair it will be good as new. So it will be good as new, showing a renewal type behavior. So in this system, the system should be as good as new, which will show a renewal type of behavior. So if the system is under perfect repair condition, then failures are according to renewal process. So then the failure are according to renewal process. So if the system is under perfect repair condition, so if it is in a perfect repair condition, then it will come in under renewal process. The renewal process is a plausible first order model for components or parts, since complete replacement of a component after failure implies renewal instead of repair. So what it is, uh, what I'm trying to say is that it is a first order model for components or parts, since complete replacement of a component after failure implies renewal instead of repair. So uh, it it doesn't mean repair, it just means renewal. So it just acts as a new system. So for a renewal process, the times between failures are independent. So the times between failures are independent and identical distributed, and repaired unit is always brought to like a new condition. So as it is renewed, it is not repaired, so it is assumed as a new condition. So for this reason, the renewal process cannot be used to a model a system experiencing deterioration or reliability improvement. So it cannot be used for a reliability improvement. It only can be used if it is renewed. It only can be used if you want to feel like a new. So these were the three point process model, that is non-homogeneous Poisson's process, power law process, and renewal process. Now I'll see the topic in the next lecture. So thank you very much.